Hello friends, today is the 15th lecture on electrostatic potential and capacitance, and today we derive an expression for energy stored in a capacitor. Then how energy can be stored in a capacitor? Energy can be stored in a capacitor by the method of charging a capacitor. And charging a capacitor, it is the process of transferring charges from one plate to another plate of a capacitor, and this can be done by using an external potential difference field or external electric field. Consider an uncharged capacitor of capacitance C. It consists of two conductors separated by a certain distance. Certain distance D. D is the distance between the two plates of a capacitor. Then when t equal to 0, that means initially the capacitor is uncharged. Therefore, at t equal to 0, q equal to 0 and v equal to 0. If there is no charge, there is no potential difference. Hence, in the first case, initially, that is t equal to 0, q equal to 0 and v equal to 0. And when a capacitor is connected to and with external battery or cell provided with a plug key. When key is closed, the circuit is closed. Therefore, the positive charges move from positive terminal of the battery to first conductor and negative charges to the second plate. When there is no potential difference, suppose that an infinitesimally very small charge of dq is lifted from plate 2 and send it to plate 1. There is no work is done, because initially plate 1 and plate 2, they are at q equal to 0. There is no charge. Therefore, no work is required to send an infinitely small charge from plate 1 to plate 2. Once a positive charge dq is brought to first plate, it acquires some potential. Therefore, to bring next small charge dq, it requires work done. And therefore, by doing work, that is, a cell spends its energy to transfer charge from second plate to first plate. Let after some small time t dash, the plate 2, from plate 2, charges are transferred to first plate. Let q dash be the charge transferred from second plate to first plate. At the same time, the second plate acquires an equal amount of negative charge on it. Therefore, when t equal to t dash means after some time, total charge on first plate is plus q dash and total charge on second plate is minus q dash. And the potential difference between the plates of the capacitor be P dash. Therefore, when T equal to T dash, Q equal to Q dash and P equal to P dash. That means work has to be done to transfer charge from second plate to first plate. And work has to be done in transferring an additional charge. It has acquired plus q dash charge. To transfer additional charge dq, work has to be done and is given by dw equal to phi dash into dq. Phi dash is the potential difference and dq it is the charge to be transferred from second plate to first plate. Then work done is given by dw equal to phi dash into dq. Here phi dash is the potential difference between the plates of capacitor and phi dash is equal to q dash upon c, because we know that c equal to q upon phi. Therefore, here q dash is the charge acquired, phi dash is the potential difference, c is the capacitance of the capacitor. Hence, phi dash equal to q dash upon c. Therefore, dw is equal to q dash upon c into dq. This is the small work done in transferring charge from one plate to another plate. Therefore, the total work done in transferring charge, total charge q, is obtained by integrating dw. A small amount of charges dq, 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 dq are transferred and sum of all dq's is equal to plus q. Therefore, adding all dw's, we can get w, or integrating dw, we get total work done in transferring the total charge q. Therefore, integral of dw from 0 to w is equal to integral of q dash upon c into dq. And integral of dq is equal to integral of dw equal to w. And substituting upper limit minus lower limit, we get w minus 0, that is w. That is equal to, here dq, q dash and dq, they are variables and c is constant, that is capacitance of a capacitor. Therefore, c is taken outside. Hence 1 by c equal to integral of 0 to q dash into dq. That is w equal to 1 by c into integral of q dash into dq is equal to q dash square divided by 2, because we know that integral of x raised to n into dx is equal to x raised to n plus 1 divided by n plus 1. Therefore, q dash raised to 1 plus 1, here n equal to 1, to q dash square divided by n plus 1, that is 2, within the limit 0 to q. Now, substitute the upper limit minus lower limit. We get q dash is replaced by q. Therefore, it is q square divided by 2 into c, minus q dash is replaced by 0. That is 0 square divided by 2 equal to 0. Hence, w equal to q square upon 2c. It is the total work done in transferring a charge plus q from second plate to first plate. And this work done is conservative. This work done is conservative, and conservative work is stored in the form of electrostatic potential energy, or the energy spent by the battery or cell. It is conservative and it is stored in the form of electrostatic potential energy. Hence, work done is conservative and is stored as electrostatic potential energy, that is W equal to U. Hence, U is the potential energy, U equal to Q square upon 2C. This is the expression for energy stored in a capacitor. Clear? And now we shall discuss the different forms of energy stored in a capacitor. Different forms of energy stored in a capacitor. We have derived energy stored in a capacitor, U equal to Q square upon 2C. Therefore, first form is U equal to Q square upon 2C, or half Q square by C. And also we know that C equal to Q upon V. Substitute the value of C in this equation, we get U equal to Q square upon 2, where C equal to Q by V, that is Q upon V. Q get cancelled, remaining U equal to Q into V, that is QV upon 2, or half QV. Therefore, second form of energy stored is U equal to 1 upon 2 Q into V, or QV divided by 2. Since C equal to Q by V, therefore here we can replace Q by CV. That is C equal to Q upon V. This implies Q equal to C into V. Therefore, U equal to Q is replaced by CV, 1 by 2 into C square V square divided by C. Here C get cancelled, remaining half CV square. Therefore, another form of potential energy, U equal to half CV square. If we know Q and C, then U equal to Q square by 2C. If we know Q and V, that is U equal to half QV. If we know C and V, then U equal to half CV square. And the energy stored in a capacitor, it is due to electrostatic field between the plates of a capacitor. Therefore, this can also be written as, if sigma is surface density of charge on the plates of capacitor, then U equal to Q square upon 2C can be written as, because we know that sigma is equal to Q upon A. Surface charge density, it is the charge per unit area. This implies Q equal to sigma into A. Q equal to sigma into A. also C equal to capacitance, C equal to capacitance of a parallel plate capacitor. Assume that the capacitor is parallel plate capacitor, and for parallel plate capacitor, capacitance of a parallel plate is given by epsilon naught A or A epsilon naught divided by D. This is the expression we have derived for capacitance of parallel plate capacitor. Substitute these values in the above equation. We get U equal to, Q is nothing but sigma A, that is sigma square A square upon 2. Here C equal to epsilon naught into A divided by D. It can be written as D divided by epsilon naught A. Here A get cancelled, remaining sigma square upon 2 into, I multiply A and D. A is the area of plates of the capacitor, and D is the separation between the plates of capacitor. And also we know that E equal to sigma upon, that E equal to sigma upon epsilon naught. E equal to sigma upon epsilon naught. Therefore sigma equal to E epsilon naught. Hence sigma square equal to E epsilon naught square into E square divided by 2 epsilon naught. Here epsilon naught get cancelled, remaining into AD, and AD equal to volume of the capacitor, that is volume of capacitor. This implies U upon phi, where phi is the volume or potential energy per into volume, is equal to epsilon naught get cancelled, remaining 1 by 2 epsilon naught into E square. This is the expression for energy density in the capacitor, and potential energy of a capacitor can be calculated by using U equal to Q square by 2C, or U equal to half Q into V, or U equal to half CV square, or U equal to epsilon naught E square upon 2 into volume, or U upon volume, that is energy per unit volume or energy density, is equal to 1 by 2 epsilon naught into E square upon 2. This U can be written as U equal to epsilon naught into E square upon 2 into volume. This is the expression for energy stored in a capacitor having electric field E, volume V, and epsilon naught is permittivity of the medium between the plates of capacitor, and energy density is given by energy per unit volume is equal to half epsilon naught into E square. Now we shall solve a problem on energy stored in a capacitor. Example, in 900 picofarad capacitor is charged using a battery of voltage 100 volt. That is, here V equal to 100 volt and capacitance of this capacitor is C. Given that capacitance of the capacitor is 900 picofarad, that is equal to 900 into 10 to the power minus 12 farad, and it is charged by using a battery of voltage 100 volt. Then what is the charge acquired by the plates of a capacitor? Your capacitance is 900 picofarad. It is charged at 100 volt. Therefore, charge on capacitor. Charge on capacitor Q equal to C into V. Here C equal to 900 into 10 to the power minus 12 into 100. That is equal to 9 into, this is 10 raised to plus 4, 10 raised to minus 12 is equal to 10 raised to minus 8 coulomb charge is acquired by the capacitor. Then the energy stored in the capacitor, energy stored, U equal to 1 by 2 Q into V, where Q is the charge acquired, V is the potential difference. That is equal to 1 by 2 Q is 900, 9 into 10 raised to minus 8 into 100 volt. That is equal to, here 2 ones are 4.5 equal to 9, 4.5 into 10 raised to minus 8, it is 10 raised to plus 2, that is 10 raised to minus 6 joules of energy stored in this capacitor. Therefore, Q with the charge stored in this capacitor. This is first case. And now, if a charged capacitor is disconnected from the battery and this charged capacitor plus minus, this is a charged capacitor to 9 into 10 raised to minus 8 coulomb is again connected to another uncharged capacitor of the same capacity, that is C equal to 9 picofarad. Then what is the energy stored by the system? When a charged capacitor is connected to an uncharged capacitor at steady state, that means when charges flowing from one charge to uncharged is stopped, that is At the steady state, both the plates acquires the same charge. Initially it is acquired Q charge, that is Q equal to 9 into 10 raised to minus 8 coulomb, and when it is connected to uncharged capacitor, then both the positive plates acquire the same charges. That means charges from charged plate to uncharged plate flow. Therefore, it acquires half of Q, and this is also Q by 2. The charge acquired by uncharged plate is Q by 2. It is also Q by 2. Initially it was Q. Similarly, the negative plates also acquire the same charge, minus Q by 2 and minus Q by 2. Let Q dash be the new charge acquired by the plates of system of capacitors. Now it is a system, two capacitors. Clear? Therefore, at steady state, when a charged capacitor connected to an uncharged capacitor at steady state, that means when charge is flowing is stopped at equilibrium position, at steady state both acquire the same charge and they are at same potential difference. That is, new charge Q dash with a new charge Q dash equal to Q upon 2 and phi dash is equal to phi by 2. Here phi is 100, phi dash equal to 50 volt. Q is 9 into 10 raised to minus 8 coulomb. Therefore, Q dash equal to 4.5 into 10 raised to minus 8 coulomb. Therefore, energy of the system of two charges, and these two capacitors are in parallel, and for parallel combination the effective capacitance is 2 times its capacitance. Therefore, here Cp is equal to 2 times C. Its capacitance increases, becomes twice, and new energy U dash is equal to 2 times Q dash into phi dash. Q dash into phi dash. That is equal to 2 into Q dash is 4.5 into 10 raised to minus 8 into phi dash is 50 volt. That is equal to divided by 2, q dash divided by 2, because u equal to half qv, that is u equal to 1 upon 2 into this is u equal to 2 get cancelled, 4.5 into 50 is equal to, that is u dash is equal to 225 into 10 raised to minus 8 joule, or it is equal to 2.25 into 10 raised to minus 6 joules. Therefore, when two capacitors of same capacity are connected in parallel, one is charged, other is uncharged, then charges acquired them, they are equal and half of the initial charged capacitor, and potential difference also decreases, and it is same for both the charges.